If this first problem was the square root of 49, we know that its value would equal 7, but we have no real number or no integer whose square is 50. So we have to try a different approach to simplify this radical. What we want to do is a factor tree and break down this 50 first into 5 times 10, and then the 10 we can break down into 5 times 2. Because this is a square root, we're looking for squares inside of that radical. And we have a pair of 5s, which really is a 5 squared. We could rethink of this as the square root of 5 squared times 2. And that 5 squared could be square rooted, and we would then have 5 root 2 as the simplification. We usually don't write this middle step that I have here, but anytime we have a pair of 5s as we have here, we would bring that out as 5. Personally, what I'm always looking to do is find squares inside of that 50. I would have taken the 50, broken it down to 25 times 2, and just right there said, there's my 5 with the 2 left over. For number 2, my fast way of doing this is to think of 108 is 36 times 3, because then I'd be able to say, 36 breaks down into a 6, or square roots down into a 6, and I have a 3 left over inside. However, most of us don't know 36 times 3 right off the top of our head when we see 108. So that's where the factor tree comes into play. Most of us are going to think of 9 times 12, which is then 3 times 3, and then we would have 3 times 4, and then the 4 would be a pair of 2s, and we would have a pair of 3s and a pair of 2s, multiply the 3 and the 2 that come out together to give us the 6, and there's the 3 that's left over that stays inside the radical. When we have a cube root, you're looking for cubes inside, or 3 of a kinds if you're doing a factor tree. Here's 54, we break it into 6 times 9, and 6 is a 2 times 3, and a 9 is a 3 times 3. These 3 3's really represent a 3 cubed, and so we can bring that out as a single 3 and have a 2 left inside the cube root. Please make sure that you do not forget to write the index down in your final answer. That is a very common mistake. Now we start to see some variables involved here. This 98, I would break it down into 49 times 2. And there we'd have a pair of 7s with the 2 left over. And then for that 8 to the 5th, there's a couple ways we can handle it. We can either go A, and say, here's a pair, and there's another pair with an A left over, and then BB, 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 with a B left over, and have 3 pairs of B's. That's the long way of doing it. And if we do it this way, we're going to have 7 on the outside, A squared on the outside, B to the 3rd on the outside, and then we'd have the square root of 2 times A times B inside, because that's what's left over. Now, technically we've said that anytime you take a square root, whatever comes out must be positive. We know 7 is positive, we know A squared is because it's raised to the eventh power, and this b cubed we're not sure of, so technically we need absolute values around that b to the 3rd. If you have directions that say assume that the variables represent positive values, then you don't have to have those absolute values around the b cubed. So I at least wanted to mention that to you. Now there is a faster way with these exponents. What I would do looking at the 5 and the 7 is I would say 5 divided by 2 and 7 divided by 2. I'm dividing by 2 because there's an understood index of 2 in this problem, and I would get 2 remainder 1 and 3 remainder 1 respectively, and that gives me the powers of 2 and 3 outside and 1a and 1b left over inside the radical. Let's deal with a 5th root. Now I happen to know the 5th root of 32 is 2, but let's say you don't see that and you go with 8 times 4, and here's a 2 times 4, I'll just bring the 4 down, 2 times 2 times 2 times 2 times 2. There's my 5 of a kind, or 2 to the 5th inside, so we know we're going to have a 2 on the outside of our answer. I would take 31, divide it by 5 because this is a 5th root, and that gives me 6 remainder 1. And I take 87 divided by 5, and it turns out that that goes in 17 times with a remainder of 2. So I'm going to have 6 x's coming out and 17 y's coming out, with 1 x left inside the radical and 2 y's left inside the radical, and I need to make sure I put my index of 5 there because it's a fifth root that we're taking. Now we do not consider absolute values for this problem at all because we took the root of an index of a radical with an odd index, and we don't use absolute values at all for those types of problems. When you have the square root of a fraction, you can square root both the numerator and denominator separately, and so in this problem we're just going to have 5 over 6, and we're done. For number 7, do not say the fourth root undoes that fourth power. Because this is an even indiced radical, we're going to have the absolute value of -4, which will be positive 4. 60 breaks down into 4 times 15. 4 is a perfect square, 2 squared. The 15 is just a 3 times 5. We can't break that down. So we're going to have a 2 on the outside of our radical, and we're going to have a 15 on the inside of our radical when we multiply the 3 and the 5 back together. Now x to the third, we can go 3 divided by 2, because this is a square root, is 1 remainder 1, and that tells me we have 1 x on the outside and 1 x on the inside. Technically, we would need absolute values around the x unless there were directions that said assume all variables represent positive values. For number 9, we're taking a cube root. Our 16 breaks into 8 times 2. 8 happens to be the cube of 2, so we actually have 3 2's coming out of it. I know I did that a little bit differently instead of going 4 times 2. So I know I'm going to have a 2 on the outside of my answer, and inside this cube root I'm going to have a 2. Now x squared cannot come out with a 3 of a kind, so that x squared just stays inside the cube root, and we can't bring any out. Now with y to the fifth, 5 divided by 3 is 1 remainder 2. So there's 3 of my y's coming out as a single y and 2 left over inside, and we don't worry about absolute values at all because the index is odd.